Next, we are going to talk about another scheduling algorithm, which is called shortest job first scheduling. It can be shorted as SJF scheduling. Remember in the previous slide, so we have talked about the first come, first serve scheduling. The major advantage of first come, first serve is that it is very easy to implement and manage. However, the downside is that due to the convoy effect, the average waiting time is quite large. But SJF scheduling is on the other extreme. So later you will know SJF scheduling has been proved that it can provide the minimized average waiting time among all the scheduling algorithm. Then let's see how the shortest job first scheduling algorithm works through an example. In this example, we have 4 processes, P1 through P4. Suppose we know the next CPU burst length for each process. Then, like I have shown you guys on the right side of this slide, P1, the burst time of P1 is 6, P2 is 8, P3 is 7, and P4 is 3. So we assume all the processes are arriving the system at time 0. Among all the processes, P4 has the shortest CPU burst length. Then P4 will be put onto the CPU first. After 3 times units, the next shortest job, which is P1, will be put onto the CPU and execute for 6 time units. Then P3 for 7 time units. At last, P2 for 8 time units. So again, we use a Gantt chart to illustrate the start and the complete time of each process. In order to calculate the average waiting time, let's see the waiting time of each process. Since P4 is the first process loaded onto the CPU, the waiting time for P4 is 0, and the waiting time for P1 is 3, P3 is 9, P2 is 16. Therefore, the average waiting time is 0 plus 3 plus 9 plus 16 divided by 4, which is roughly equal to 7. So later, after we learn other scheduling algorithms, so you can apply them to this example, you will know that no one can provide shorter average waiting time than SJF scheduling algorithm. Just like we already mentioned, SJF has been proved to provide minimized average waiting time among all the scheduling algorithms. So in order to use SJF scheduling algorithm, one challenge is that, so how can we know the next request CPU length of each process? So you may think to ask the users. For example, when you use Word software to do your writing assignment. So if I ask you that how long you can finish the assignment, perhaps it is hard to answer this question, right? And also, if multiple users use the same computer system, actually some users can cheat. So for example, one user knows that the next CPU burst time will take 100 time units. So since the user knows the scheduling algorithm used by this computer is SJF, so it just tells the system that its next burst time is a 1 time unit. Then this user will be put onto the CPU immediately. However, the overall performance of the entire system will be dramatically decreased. So actually, it is difficult to know the next requested CPU length of each process. In other words, this is the drawback of SJF scheduling algorithm. Next, so we will talk about that in practice. So how can we use some mechanisms to address this problem? To address the issue of how to determine the next CPU burst length for each process, we can predict the next CPU burst length to be similar to previous length. Then we can just pick the next process with the shortest predicted CPU burst time. the mechanism we are going to use is called exponential average. So let's define Tn as the actual length of nth CPU burst, tau n plus 1 as the predicted value for the next CPU burst. And we also define a special parameter alpha in range between 0 to 1. Later, we will explain how alpha can impact the value of the prediction. Then the next predicted CPU burst time can be calculated with the formula tau n plus 1 equals to alpha times Tn plus 1 minus alpha times tau n. Actually, it is a linear combination between Tn and tau n. Commonly, we will set alpha to 1 over 2. In this slide, it shows us an example that the prediction of next CPU burst length. At the very beginning, we predict the CPU burst time is 10, this one, and the actual CPU burst time is 6. Then we can use 10 and 6 to calculate the next predicted CPU burst time is 8. Actually, we just use 10 plus 6 and then divide by 2. And then we can get 8. Then after we know the next actual burst time is 4, then we use 4 and 8 to predict the next CPU burst time, which is 6. Means we use 8 plus 4 divided by 2, and then we can calculate 6. So we continually do the predictions, then we get those predicted CPU burst time. In the above figure, the blue line shows the predicted CPU burst time, and the dark line shows the actual CPU burst time. So for this figure, you can see that the predicted blue line is reasonably close to the actual dark line. In this slide, shows us an example of exponential average. So first, let's see two extreme cases. The first case, the alpha has been set as 0, then tau n plus 1 will be equals to tau n, which means recent history does not count. The next predicted CPU burst length only depends on the previous predicted length. The other case, the alpha has been set as 1, then tau n plus 1 will be equals to Tn. In this case, only the actual last CPU burst length is counted. As we have mentioned in the previous slide, commonly the alpha value will be set as 1 over 2, which means we take the equal weight to both previous predicted value and the actual value. Then let's briefly explain why it is called exponential average. If we expand the formula, we will get this. After we expand this formula, so we can see that the weight of the historical record will be decreased exponentially as alpha and 1 minus alpha less than or equal to 1. Actually, each successive term has less weight than its predecessors.